The last time we completed chapter 6, I believe, which was chemical energetics. And today we'll be starting with chapter 7, and that is titled Chemical Reactions. Right, and in this we will learn what is termed as a chemical reaction, although we already know that, but still they'll talk about it formally. And we are going to learn about factors that influence the rate of a chemical reaction, and reversible reactions, we're going to learn about equilibrium, and then we're going to learn about the industrial manufacture of ammonia and sulfuric acid. Right, so first of all, let's start with chemical reaction. So chemical reaction right, is one that results in the formation of something new, and in most cases, right, it is non-reversible, meaning, right, it only goes one way. From reactants to products, right? And so once you get a new, right, a new, substance, you cannot go back, at least not, you can't go back easily, right, to regain the initial reactants. So once a new product is formed, right, the reactants cannot be regained, right, and I'm putting an asterisk over here, easily. In some cases it cannot happen, in some cases to do it, it is very difficult, right? So for example, how difficult would it be? Let's say you reacted, right, NaOH and HCl, and you got NaCl and H2O, right? So
Yeah.
right, how do you go back? How do you regain? Like how do you split this, right? You can't. Like we've studied in electrolysis that to split the sodium and the chlorine, right, you need to perform electrolysis. And electrolysis is not easy. Now that is to split the sodium and the chlorine, right? Not to regain. Right? So there might be another pathway to, split this and then regain, but it's not going to be easy, right? At least, or it's going to take a number of steps. So you just can't go, oh, I'm going to dissolve salt in water, and that will give me sodium hydroxide and hydrochloric acid. That's not how it works, right? So it's not simply going back and pressing the rewind button or something. Okay, so you can get those things back, and then once you split this, you get the sodium and the chloride and the chlorine. And then, right, what you can do is you can react this with water, right, to get sodium hydroxide, and you can react this with hydrogen to get HCl, and then dissolve it in water to get, so it's a long process, as you can see,
Yeah.
right?
Yeah.
So, right, this is different from a physical change, right? A physical change is a change in state, such as melting, right? And so you've got ice that melts to form water, which is a liquid. And a physical state is reversible, right? So the sign that you use for reversible reactions is you draw half arrows both ways. So you have this, that's a half arrow, and then this, right? So this is the sign of something being reversible, right? And so this is a change of state.
Yeah.
So if ice is melting to water, you can freeze the water and turn it back to ice, and right. So there is no chemical change taking place, right? Chemically, ice is H2O, water is H2O. There's nothing new being formed over here.
Yeah.
Okay, so that's the first thing they want to clarify. What is a a physical change as opposed to a chemical change? Okay. Now, reactions can be fast or slow, right? Some reactions, like the examples they give. So I'll just write that down. Chemical reactions can be slow. For example, the ripening of fruits. So the ripening of fruit on the outside doesn't seem a chemical reaction, but the reason why fruits ripen is because there are chemical reactions going on inside.
Yeah.
Okay.
Uh, yeah.
And then you've got some that are at a moderate pace, can be slow, they can be moderate. For example, the burning of fossil fuels such as coal, right? So the burning of coal, we know that combustion is a chemical reaction because, right, you talked about combustion in the previous chapter and how it produces carbon dioxide and all of that. And they can be fast, right, such as explosions, right? So explosions, basically the one reason why explosions happen is because the reaction happens so fast and it's so exothermic that it just blows up, right? So that sudden release of energy, because that's what's happening in exothermic reaction, right? Heat energy is being released, and so the
Yeah.
reaction happens so fast and so much heat energy is released, there's an explosion. Okay, just like
Yeah.
an explosion happening in a gas tank, for example, right? So if you use it like nominally, right, it's a moderate thing, you're burning the gas and you're using it to cook or whatever else you're doing with it. But if there's like a spark in the gas chamber, and so all of that gas will ignite together, and it's so exothermic, it's so sudden that it will blow up.
Yeah. Okay.
Okay, all right. So, right, industrially, right, techniques are used to control chemical reactions, right? Industrially, you don't always want the reaction to be very fast. Need to be balanced, right? Balance in the sense between their rate, their yield, so how much you're getting out of it, right? And other factors such as temperature, cost, right? So you don't want something happening very fast necessarily, right? If it's happening very fast, maybe you're not getting a good yield, right? Maybe the temperature needs to be very high, which is going to cost a lot, or there are other factors, right? You can't contain that temperature. And so industrially, there's a balance that is found, right? That you've got chemical engineers and other guys, right? Chemists and everything, and they try to find a balance where you can have a reaction happening that's going to give you sufficient yield, like sufficient amount of product, right? So yield means amount of product that you're getting,
Okay.
right? And the temperature is manageable, and the cost for the entire thing is something that is economical, right? So the amount of money you're putting in, you're going to get more back, so you're actually running a profit, because
Yeah.
no one's going to work at a loss, right? Or even break even, because then I'm not gaining anything out of it, right? So anything that's happening industrially or commercially is obviously for profit, right? it's
Okay.
it's it's not, right, for the well-being of humanity.
Yeah.
So there are five main ways in which the rate of a chemical reaction can be altered and controlled, right?
Mm.
Right, and those are, drum roll, right? What are those factors? The changing the concentration of solutions. So I'm not going to write changing concentration of solutions. So this is for when you've got the reactants as liquids, because the solution applies to liquids, right? Aqueous solutions. You are,
Yeah.
right, changing the pressure of a gas. So pressure applies to gases. The surface area of solids. So surface area applies to solids. Just a sec, sorry. So after surface area of solids, you have the temperature, and then you have adding or removing catalyst, right, including enzymes. Right, so these are the five things: concentration of a solution, pressure of a gas, surface area of solids, temperature overall, and catalysts. So these are things which can be used to alter the rate and control how the reaction is progressing. Now, before we get into talking about any one of these, the first thing we want to talk about before that, to understand how each of these has an effect, right, is the collision theory. So this is a tie-in to the kinetic particle model, right? And so what this means is, right, all substances are made up of particles. So they're made up of atoms or molecules, right? So all substances are made of atoms or molecules, right? And that obviously that holds true for our reactants in chemical reactions as well. And so what happens in a chemical reaction, the particles of the reactants collide with each other, right? And so one thing is the collisions that are happening, right? If the particles have the minimum amount of energy for the reaction to occur, which we talked about at the end of the previous class, which is the activation energy. Do you recall activation energy?
Yeah.
If particles have the minimum minimum amount of energy required for the reaction to occur, right, products will be formed, right? And so this is called a successful collision. So there's a difference between collisions, right? The number of collisions overall, just because they are colliding doesn't mean that it's going to happen, because they need a specific amount of energy for them to actually, uh, react and form the product, whatever it is, right? And so if that is happening, then that's successful collision. So you need to keep these two things in mind, right? It is number of collisions versus number of successful collisions. Do you understand the difference?
Yeah.
Right? And so these have the required minimum, which is called the activation energy, the EA. All right.
Yeah.
And so going back to that diagram, right? This. So you've got methane and oxygen. This is the activation energy to get it started, right? And then it goes on to form the products. And so the enthalpy change as well. So just recall is the change in the energy of the reactants and the products, right? So the enthalpy changes from the level of the reactants to the products, whereas the activation energy is just how much you needed more to get things started. It's different from when you have an endothermic reaction, right? This is exothermic, obviously. So it's different when you have endothermic reaction, but this is what it looks like, right? So that's activation energy, that's the enthalpy change. Okay. Now let's talk about each one of these in turn. And we are starting off, the first thing they mentioned was concentration, but the first thing they're going to explain is, right, surface area. So it doesn't matter, right? There is no sequence to these. Again, surface area relates to solids, concentration relates to solutions, so it's all good. So surface area, how does that help? And so basically the surface area of a solid, right? For example, you have this lump over here, right? In fact, let's make it a bit bigger, makes it easier, right? And if you're reacting this, for example, if you are, let's say, washing this, you're putting water on it, water will only be, accessible on the surface that is exposed, right, which is this, right?
Yeah.
And so it's not going inside anywhere, right? This is like a solid block, it's not going inside anywhere. But what if you were to cut it up, right? What if you took this block and you made it smaller, right? So you cut it up into 4 blocks. Assume that this is the same size of that block. and now you're washing it with water, let's say, right? And so now water is obviously coming on the external surface that was available before, but it's also going in between. And so this is extra surface available to be washed, isn't it?
Yeah.
And so you apply that same concept, you make it smaller. And so now you've got even more. So you've got that external surface that you had initially, right? And you've got even more. So all of this, right? I mean, I left a gap over here in between, but anyway, right? You could like make some more
Yeah. Yeah.
just to fill that up. Okay. And so, right, the finer it is, the smaller the granules are physically, right? We're not talking about particles in the sense of atoms or molecules. The finer it is physically, the more granules there are, the more surface area there will be, right? So the finer the solid is in terms of its granules, right, the more surface area is available. And so I talked about washing in water, right? Now assume that you are reacting it, you're putting this into a liquid. For example, you are putting a metal into water, for example, right? We've talked about that reaction. And so what would happen, right, if you put a lump of metal into a liquid as opposed to you put granules, right? So you've got a lot more surface area for the reaction to occur, and so it's going to occur very fast, right? This will also
Yeah.
occur, it's just going to be slower, right? So it's going to be comparatively much faster because there's more area on the reactant, on one of the reactants, on the solid reactant, available for the particles of the other one to come in, collide, have successful collisions, and form the product. Does that make sense?
Yeah.
Okay. And so that's what surface area is about, right? And so what they do, I'll take you to the book for this one because this, like I don't really feel the need of explaining this on the whiteboard, right? So if the concept is clear, then they give the example of putting a lump of calcium carbonate, which is a solid, into hydrochloric acid, which is aqueous, right? And so what you have over here, if you can just see that, if I zoom in down here, this was a lump, right? And so you can see that white calcium carbonate at the bottom, right? The reaction is slow. What you expect,
Yeah.
we've talked about reaction of carbonates with acid, and so what you get is the release of carbon dioxide gas. And you can see not much is happening over here. Whereas in this test tube, they put finely ground calcium carbonate, right?
Yeah.
And so the reaction was fast, and you can see all this gas bubbling up, right? So that's all the carbon dioxide that's being released. And
Yeah.
right, so this is just showing that the reaction is faster, right? So there are two ways that the rate of reaction can be measured. So I'll just show that to you. You can see the measuring scale over here, and you can also see what happens eventually, right? Is all of it will eventually, uh, you know, the reaction will go to completion in the sense that all of the calcium carbonate will eventually react with the hydrochloric acid, and right, whatever amount of carbon dioxide gas is to be given off will be lost, right? In this case, right, 2 grams is lost. But as you can see that in case of the powdered limestone is calcium carbonate, it was lost much quickly. So it was lost at about 3.75 minutes. So that's 3 minutes and 45 seconds approximately. whereas it took nearly 5.5 minutes, a little more, for the lump to lose that same mass. So all of it did
Yeah.
react, it just took longer. So increasing the surface area, right, increases the rate of reaction. Now in this case, going back to the whiteboard, just a sec. There we are. So in the case of, you've got HCl plus calcium carbonate, right? And right, that reaction will give you calcium chloride and carbon dioxide and water. Right, and to balance this out, you just need this over here. This is aqueous, this is solid, and right, the calcium chloride is also aqueous. This is a gas, and this is a liquid. So how do you measure the change or the rate, right? So in this case, rates of reaction can be measured by either, right, the volume of carbon dioxide given off, right? So it's a gas, so the volume of carbon dioxide gas produced, so you measure that, or the loss of mass in the mixture.
By the way, we won't be doing the balancing one, right? With this equation.
I mean, it's already balanced.
Yeah. Okay.
So loss of mass of the reaction mixture, right? And so why is the reaction mixture losing mass? Can you tell me?
Could you repeat that?
Why is the reaction mixture losing mass?
Haram, I'll let you handle this one.
Mm-hmm.
Yeah.
Yes, Haran. Can you tell me why the reaction mixture is losing mass?
I don't know.
Because of the carbon dioxide
Maybe
gas.
because of the surfing. Oh.
It is a gas, it is going off, right? It is being released, it is going, it's not going to stick around, right? This carbon dioxide gas is coming from here, isn't it?
Yeah.
Right? So there's a loss in mass, this gas is escaping, right? And so what you do is you put that conical flask, right, on a electronic balance, and you, with time, like every minute or every 30 seconds, you take the reading. Once you put in the calcium carbonate, right, you take the initial reading. There's HCl in here, you put in calcium carbonate, you take the initial reading, and then you take a
Yeah.
reading for every 30 seconds, right, until it doesn't stop. And so that will be the final reading. And so, right, you plot a graph, as you saw, of, right, time on the x-axis versus loss in mass, right, on the y-axis. Okay, and so that will tell you, and you can do this for, the lump versus the powder, and you see basically right? You're focused on how quickly it happens. So you're noticing, right, that time factor. Is this clear?
Yes.
Yes, Aram?
Yes.
Okay. Do we have time? Can we talk about concentration?
Yes, we can.
Right. And so they mentioned that, you don't always want this to happen because in certain industries where they are dealing with fine powder, like the cement industry, it is also dangerous because it's so fine that it can easily and very quickly and very, rapidly react. And there have been cases where explosions have happened just because of that, right? They give the example of explosions happening in a flour mill in Jamaica back in 1988, right? So it was wheat, it was flour, but because
Yeah.
it's fine and everything, whatever the situation was, the storage silo, as it's called, it exploded, right?
Yeah.
So yeah, that is problematic.
Yeah.
Okay, I'm going to skip concentration for the moment, and just for today, I'm going to talk about pressure, right? Because pressure and then, right, how much time do you have on the clock?
Uh,
22.
10.
Okay, yeah. So I will talk about concentration then. So concentration is to do with solutions, right? And the concept behind it is if you increase the concentration, that means you've got a greater number of particles of the reactant, right? And so if there's more of the reactant, then that will increase the rate of the reaction. Why will it increase the rate of the reaction? Because with more reactant, you'll have more collisions,
Yeah.
right? And therefore, there's chances of more successful collisions. Make sense?
Yes.
Okay. So that is the concept behind it. Now, what's the experiment that they do for this, right? So what they do is they take two liquids. One of them is sodium thiosulfate. So sodium thiosulfate plus hydrochloric acid, right? And that gives you sodium chloride. And right, sulfur. Let me just and sulfur dioxide. So there are a few things forming here: sulfur dioxide and water. Right, so all of that. What does it look like in terms of its equation? You've got Na2S2O3, so that's sodium thiosulfate, and that's aqueous. Then you've got 2HCl, which is also aqueous. You are getting sodium chloride, which is also aqueous, right? You're getting sulfur as a solid, sulfur dioxide gas, and obviously water, which is a liquid.
Yeah.
And so what happens in this is initially, right, the solution is clear. Right? But as reaction progresses, it it a yellow color develops,
Yeah. Okay.
and that yellow color is the sulfur, the solid sulfur that is precipitating, right?
Yeah.
And so what they do is that they put the conical flask. Well, that's actually a round bottom. So uh, yeah, you put the conical flask on a piece of paper, right? And on that paper, they've put an X. So when they put the conical flask, it's made of glass, which is clear. The solution inside is clear, and so they can see that X, right? And as time passes, the reaction progresses, and you're getting that yellow color, that sulfur precipitate. What they notice is that, right, you can no longer see the X, right? So you got this. I have the yellow color, so yeah, it turns yellow, right? And so they
Yeah.
notice, right, they time it, and so they measure the time taken for the cross, so that X is called the cross, to disappear, so it's no longer visible. Then they repeat the experiment, right, at with different concentrations of sodium thiosulfate, so that's Na2S2O3, right? And then they time it as well, right? And what they notice is that the higher the concentration, right, the faster is the rate. Well, the lesser time it takes, let's say less time for cross to disappear,
Okay.
right? Because the reaction is faster.
Yeah.
Make sense?
Yes.
Okay. And so what they do is that they plot a graph of time taken for the cross to disappear versus the concentration of sodium thiosulfate. And obviously, as you just talked about, the higher the concentration is, the less time it will take. And so basically, right, what you plot a graph, and the graph will look like this, right? So it will be like a curve that's decreasing, right? You got concentration and then you got time over here, right? So I'll show that to you in the book. What you can do over here is that you can find the rate. So the time taken is not the rate, right? So you can find out the rate of reaction for each repeat of the experiment. So you can find out the rate of reaction for each concentration of this sodium thiosulfate, where this is the formula: rate equals to 1 upon time, right? So time of reaction in seconds. So you divide 1 by however long it took for the reaction to occur in seconds. In this case, how long it took for the cross to disappear in seconds. And when you do this, now you can plot a graph of concentration of sodium thiosulfate versus the rate, not the time. And so in this case, you initially had a curve. In this case, you will get a straight line, and a linear straight line is much easier to deal with, right?
Yeah.
So let me show that to you in the text. So there you are, right? You see, this is concentration of sodium thiosulfate per mole per decimeter cube. What that means, right? The mole and everything, we'll come back to that later. and then time for the cross to disappear in seconds, right? So they've got it all from 0 to 120. And so as the concentration is increasing, the time is decreasing. Then you take the rate, and so obviously you're going to get these decimals, right? It's going to be small, but anyway, right? And you still have that same concentrations, but this time you are getting a linear graph, which is easier to deal with. It's more, suitable. And so the concept behind it is, right, as a result of the collisions between reactant in a more concentrated solution, there are more particles, which leads to more frequent collisions between the reactants, right? And then often they have enough energy, which means they have enough, they can reach the activation energy, and so you're going to get more successful collisions, and that will increase the rate of the reaction and it will take less time. All right.
Yeah.
Okay. I'm going to. Do you want to go on? We still have a few minutes. We got like 10 minutes or so.
Uh,
I'll just quickly do pressure.
okay.
Okay, because there's not much to talk about. So pressure of a gas, right? And so basically what's happening when you're talking about the pressure of a gas is when you increase the pressure, right? At which the reaction is being carried out, in which gases are involved. So increasing the pressure of a gas, right? Or in fact, right, the pressure at which the reaction is being conducted or the reaction is occurring, it's taking place. And obviously the reactants are gases, or at least one of them is a gas. And so what that does is it pushes, it sort of compresses the gas particles closer together.
Okay.
Right? And so that means that you are increasing the number of particles per unit volume. So when you're increasing the pressure, the volume is going to go down. Right? And so when the volume is going, you have the same number of particles in lesser volume, right? And so that's increasing the number of particles per unit volume. And what that's going to do is that you're going to have more frequent collisions, right? So you're going to increase the collisions, right? And that would lead to more successful collisions, hopefully. And that would increase the rate of reaction. Make sense?
Yeah.
Right? And so they haven't given an example for this one. That's all they've explained for it. But when we talk about the manufacturing of ammonia and also sulfuric acid, this will come into play, right? So we'll see the pressures at which they are taking place and the temperatures and everything else. Any question?
No.
Right, so tomorrow we'll talk about how temperature affects the rate of reaction. There's not a lot to talk about. You can probably guess, right? Kinetic particle theory, more temperature, more energy, particles moving around faster, right? More collisions. You get the idea, right? So catalysts, we're going to talk about those, and then enzymes, and then we'll follow that by, I think, equilibria and reversible reactions. I don't know if we'll be able to cover the manufacture of ammonia and sulfuric acid, but that's fine. Right? We do have a good pace in chemistry, so I think we'll be okay. So yeah, see you guys tomorrow then.
Inshallah. Okay. Allah Hafiz.
All right, Allah Hafiz.